Okay, you went over the front cover page with the guest teacher, but I want to highlight just a couple things here. Your job is to get the ball to go in the hole, but instead of as few strokes, we want the least distance, so the shortest lines possible, shortest distance. It can start anywhere in the start, but when your ball bounces off the wall, it leaves the wall in exactly the same angle. So the angle of entry must and the angle of exit are congruent, which you can see these two angles are congruent. So I am going to show you an example of how you want to start this out. Now you're going to need a protractor and a ruler, and don't be surprised if you don't get it on the first try for a hole. It's actually kind of a challenge to estimate what angles it will take to get the ball to go in. So if you draw your starting line, start anywhere in the starting area. First you want to draw your path before you actually figure out any distances here. So I'm going to get my protractor. Okay, and if I drew my first starting line, remember the ball has to bounce off at the exact same angle that it entered. So if I look here, it entered at about 33 degrees. So I'm going to go ahead and draw a line that is 33 degrees off of that wall. Go all to the other side of the wall. So now hopefully when I draw the next line it will go in the hole right here. If not, I'm going to have to readjust, go all the way back to the start. You always want to draw your lines nice and light before you do any calculations. So I'm going to measure the angle that the ball entered the wall at, and I see that's about 56 degrees. So I will now draw a 56 degree angle, and it just barely goes in the hole. So once your path goes in the hole, it is now your job to figure out distances using trigonometry, which you're going to need your angles again. It would be helpful to write these down, but if you have to go back and measure them, you do. So this angle here was 33 degrees. 33 degree angle. And remember, you're trying to figure out the distance of the path of the ball. So this distance plus this distance plus this distance here. Okay, well if I have a 33 degree angle, I know the length of this side is one box equaled 1 foot, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, because I am using this as my right triangle. Okay, I know I'm trying to find the hypotenuse, and in comparison to the 33 degree angle, I have the opposite side. So opposite over hypotenuse, that would be the sine function. So if I take the sine of 33 equals the opposite side length, 15, over the hypotenuse, which is x. We're not sure right now. I'm going to find the sine of 33, 0.54, multiply by x, so I have 0.54 x equals 15, divide by 0.54, so 15 divided by 0.54 is 27.8. So that is this distance right here. Okay, again, I know that this side is 33 degrees. Okay, and I have my units right here, so 5, 10, 15, 20, maybe 19 and a half. You can round to the nearest half a unit. So this length is 19.5. So again, compared to the 33-degree angle, the sine is the opposite, 19 and a half, over the hypotenuse, which I'll call this side y. So I'm going to show my work in here. So the sine of 33 equals 19.5 over y. Well, I already know the sine of 33 is 0.54 equals 19 and a half divided by y, multiply by y. So I have 0.54 equal y equals 19 and a half. Divide by 0.54. So 19.5 divided by 0.54 is 36.11. So that is this side right here, 36.1. Okay, and last but not least, I have to figure out the last side length right here. So I need to measure this angle, or if I know that it is congruent to this angle, instead of going back and measuring it, I can do 180, take away 33, take away 90. That gives me a 57-degree angle. So this is also 57. And if I'm going to quick draw in a right triangle here so that you can see the triangle. I have a 57-degree angle, and I know this side is about 5, 10, 15 units long. It just so happens that I already had 15 and 15, but you have to be careful. You're talking about a different angle and a different side length now. So we're still looking for the hypotenuse, but now we have the adjacent side compared to the 57-degree angle. So adjacent over hypotenuse is cosine. So I will take the cosine of 57 equals the adjacent side length, 15, over the hypotenuse, I will call m. So cosine of 57, 0.54 equals 15 over m, multiply by m, so 0.54 m equals 15. Last step is to do 15 divided by 0.54. You get 27.8. Now if you notice something, it just so happened that on this one, this ending triangle was congruent to the beginning one because I had two side lengths of 15, and I actually had two congruent angles. This angle is 33, well it happens that this one is 33 because of the triangle sum theorem. So this one is also 57. But your last step then is to add up all three distances, or how many ever strokes it took you to get to the hole, and figure out what your final distance is. So 27.8 plus 36.1 plus 27.8 is 91.7 feet. And make sure you put that somewhere on your paper so you can easily find it when you have to go add up your total. Okay, so you might have to try quite a few attempts to get your ball from the starting point to the hole. because if you try drawing your angles and you get all the way to the end and then it misses the hole, you gotta go try a new starting point with different angles. But one thing I found, if you're really stuck and you've tried a couple times, try reversing it. Try starting at the hole and going to the starting point. So if you start at the hole and go to the starting point, then you'll for sure get in the hole. You just have to hit this bigger starting point target instead of the smaller hole. And don't forget that all of the angles, the input angle and the output, are all congruent. Draw your lines lightly so that it's easy to erase. Good luck with the project and do your best. Don't forget to show all your work in the margins of the paper. If you need extra paper, just use some line paper to show your trig calculations.